Hello everyone. This lecture can be thought as the introduction to our course, Advanced Communication Techniques. So in this lecture, we are going to briefly discuss about the history and the future of wireless communication. And also at the end of the lecture, we will have a short discussion about the topics we plan to cover in this semester. Now the textbook that is referred for this lecture is this one. So without further ado, let's begin. First of all, let's talk about some of the early inventions of wireless communication. The first invention that led to the wireless revolution that we are seeing right now is the invention of electromagnetic wave propagation done by James Clerk Maxwell. So in 1864, he discovered this phenomena, and after this discovery, there were many applications in the fields of science and technology using this invention of electromagnetic wave propagation. One of those applications, a very important one, was the invention of radio propagation. So in 1897, Bose and Marconi, they both performed the first wireless radio transmission. After this invention, slowly but surely, this radio technology was getting popularized and commercialized. Specifically, it was developed for military and transportation services in the year of 1930s and later. But the problem is, there was no specific technology for efficient use of wireless spectrum. Like now we have multiplexing, multiple access, cellular concept. These kind of things were not available at that time. As a result, this technology was very costly to use, and this radio was used only for the essential service at that moment. Afterward, in the year of 1947, Claude Shannon did a publication on the mathematical representation of wireless communication channels. That was a very important contribution to this field. After this publication, this led to some other inventions like frequency reuse technologies. So this was one of the first solutions for spectrum scarcity, and further this developed the concept of cellular. Now we know that our modern communication or modern mobile communication is based on this cellular concept. Now this cellular concept was established in Bell Laboratories in 1960s, and after that the first cellular telephone network was established in 1979 in Japan. After the deployment of this first cellular telephone network, these mobile telecommunication systems were getting fully commercialized. Like we had the first generation 1G, then 2G, 3G, and right now we are experiencing 5G, right? So these things happened afterwards, after the invention in 1979. Now let's discuss briefly about these generations of wireless communication. That means starting from 1G up to 5G. So roughly about in every 10 years we have a new generations, like 1G started in 1980s, right? So 1G in 1980s. 2G was deployed in 1990. 3G was deployed in 2000, like this, right? And 4G in 2010s, and right now we have 5G. The exact deployment time was 2019, but it can roughly be thought as 2020, right? So roughly in about 10 years we have a new generation. So let's talk about the first generation of wireless standards. This first generation of commercial cellular network was fully analog. That means in the first communication course you have learned about the analog communication modulation techniques like AM, amplitude modulation, frequency modulation, FM. These kind of things were used in 1G. Specifically AFM was used, frequency modulations, and the data rate we had at that time was not that good, which was 2 kbps only. And we had standards like AMPS. So what is standard? Standard is a kind of full-fledged communication system, you can say, where we define all the specific parameters, like what are the frequency range we are going to use in that standard, what is the modulation technique we are going to use. So these kind of specific things were defined in a standard, and that was deployed as a full-fledged communication system. So that time the standard which was established was AMPS, Advanced Mobile Phone System, and that was FDMA based, that means frequency division multiple access based. Now let's move on to our 2G wireless standard, which started from 1990s. So unlike 1G, 2G was not analog, it was fully digital, or the first digital communication network, you can say. Previously, whatever we have seen from the very early beginning up to 1G, everything was analog. And for 2G, the main purpose or the main goal was to provide voice communication facility only. So there were many standards. You have to understand that for each of the generations, not only one standard is established, several of them are indeed established as the time progresses. So initially, when in 1990s, two standards, GSM and IS-95, these two were deployed, and that had a data rate of 10 kbps. Afterwards, with the progress of technology, we had 2.5G, and the standard was GPRS, and the data rate for that was 50 kbps. So as you can see, at the end we had 2.5G standard of age, and with a data rate of 200 kbps we could do more than just voice communication facility. So that happened. So even though initially the goal of 2G wireless standard was to provide voice communication facility only, afterwards we had the capability to provide low speed data access like internet or email. These kind of things were possible with 2G. Then move on to 3G wireless standards, which started from 2000. So one of the key techniques used in 3G wireless standards was the CDMA, or code division for multiple access. Previously we had used FDMA or TDMA. FDMA was predominantly used in 1G, and TDMA was used in 2G. In 2G, CDMA was also used, but not that predominantly, but in 3G it was used heavily, and it had a very superior quality compared to TDMA and FDMA. That's why we had much higher data rate. If I want to look at the standards and their data rates, so these are the standards, and up to 5 to 30 Mbps, this kind of data rate was possible with 3G wireless standards. That means we could provide much more than just voice or even internet. We could provide high transmission data rate, real-time video conferencing. These kind of things were possible in 3G wireless standard. Up to this day, we are still using 3G in parallel to 4G and 5G, right? So afterwards, let's talk about the 4G wireless standards, which started from 2010. So at that time, we had two key revolutionary techniques we used in 4G was orthogonal frequency division multiplexing, OFDM, and another one is the multiple input multiple output, MIMO. So obviously in this course we are going to discuss about these key techniques used in our cellular mobile communication in detail. So these two techniques had a far more superior quality compared to the previous ones like CDMA or TDMA, FDMA, these kind of techniques. That's why we had a much more higher data rate compared to the other generations, the previous generations. So we had up to 1 Gbps data rate at the end, which is the standard of LTE advanced. So as you can see, right now we are using these kind of standards. So LTE is heavily used in our mobile communication systems, and we can do much more than just voice communication or even internet. Now real-time data transmission or high data transmission is possible, like online gaming or HTTP. These kind of things are possible because we have a data rate more than 100 Mbps, right? Now let's move on to 5G wireless standards, which is currently under evolution. Now 5G started its journey from early 2019, and what you have to understand here is for each of the generations the development begins 10 years earlier. That means the development of 5G wireless standards began at 2010. The development of 4G began in 2000, like this. So 10 years earlier. So they take 10 years to develop a standard and then deploy it. Okay, then like 4G, 5G also uses OFDM based architecture, but in parallel to that it uses massive MIMO, which is a version of MIMO, and also millimeter wave communication sometimes. And also there is another technique called NOMA, non-orthogonal multiple access. This will be deployed or added as a feature in 5G maybe in future, as we don't have enough computational power right now in our mobile phones. That's why that is not a very viable option, NOMA. That's why we only use massive MIMO, OFDM, these kind of things in our 5G wireless standard, and we have a very good amount of data rate in 5G, and slowly it is getting deployed everywhere worldwide. And 5G can deliver up to 20 Gbps, which is a huge amount of speed. And the application for 5G, or the goal for 5G, is to enable it for virtual reality, IoT, artificial intelligence, this kind of thing. And a very important one is the M2M, or machine to machine communication. That means all our devices should also be connected to our network, like household appliances can also be connected with the network for our better service, right? Now let's look at this figure. This figure was taken from your one of your textbook, multi-carrier techniques for 4G mobile communications. Now unfortunately this book was published in 2003, which is very early. So they try to predict what will happen in the future, like in 4G or 5G, what may happen, what are the techniques we may use. These kind of things are actually illustrated here. So they said that in 1990 for 2G system we had two candidate techniques. One of them was CDMA, another one was TDMA. At that moment we didn't have computational capability or whatever to handle CDMA. That's why we adopted TDMA as our standard, right? But afterwards in 3G system we had two candidate techniques, OFDM and CDMA. At that time we adopted CDMA instead of OFDM, and they predicted that in the 4G system that's why we are going to adopt OFDM, because in the previous generation we had OFDM as a candidate techniques. Also they said that there should be another technique which is MIMO, right, for 4G system. Indeed they were true. That means in 4G system we had two candidate techniques at that time, OFDM and MIMO. OFDM was first adopted, and in the meantime afterwards MIMO was adopted as well, like in 2015 or 16. In that time we had MIMO also established for 4G system. And in 5G system they predicted that this MIMO will be adopted as well, because in previous generation MIMO was not adopted. Actually for 5G system we had two candidate techniques. One of them was NOMA, or non-orthogonal multiple access, and another one is this MIMO. MIMO was basically adopted. We don't have right now, we don't have enough computational power to handle NOMA. That's why maybe in 6G we will have NOMA as our standard, right? Maybe. Now for all the generations that we discussed earlier, the main goal was to, or is to, increase the number of users that we can serve, and also increase the throughput. That means the data rate we are giving to each of the users, and increase the coverage. That means the area we cover using each transmitter. So Actually, we have several technologies that we have earlier discussed. They help us to achieve those things by optimizing the spectral, temporal, and also spatial allocation of wireless resources. So spectral means the frequency allocation, and temporal means in time domain how do we allocate the resources for each of the users or among the users. And spatial allocation means the cellular concept that we have heard, that is an example of spatial allocation of wireless resources. So now there are several technologies that we use currently that are helping us to achieve those. We have already talked about those. I mean, at least we know the name of those techniques like OFDM, CDMA, MIMO, massive MIMO, and NOMA. Now I am going to briefly discuss about those things, and obviously we will have a very detailed discussion about each of these topics. This is the goal of our course. In this course, we are going to see the working principle of each of these techniques and how they work, how they are deployed, these kind of things. So first of all, let's discuss about orthogonal frequency division multiplexing, or OFDM. We have already said that OFDM is a key technology in modern wireless communication. That means in 4G and 5G it's heavily used, and it can support data rates up to 100 Mbps. But how does this OFDM work? If I want to briefly discuss that, let's say we have a signal X that we want to transmit, and we all know that we have to use some kind of modulation techniques to transmit that data into our wireless channel, right? So after modulation in the frequency domain, it should look something like this. So this is our frequency domain. So let's say it has a bandwidth of B. So it will have a bandwidth of B after this modulation, right? So we use carrier signals to modulate this signal X. So this is the traditional process how we take a data and modulate that to send it into our wireless channel. Now let's say instead of sending this whole data X, we divide this into small portions like X1, X2, X3, like this, right? Up to, let's say, X of n. So then we can use several subcarriers instead of the single one. So for each of them we will have one carriers to send them to our wireless channel. Then it should look something like this. In the frequency domain it should look something like this. We will use the same bandwidth of B, but now we will divide it into n portions, something like this. So this is for X1, this is for X2, this is for X3 up to X of n. So instead of using one carrier, we are using multiple carriers to transmit the small portions. At the end we are sending the whole data because X1 up to Xn constitute X. So this is one concept of OFDM. Okay. So in reality we don't even send it like this, we overlap the carriers. So it should look something like this. So one carrier overlaps another one, like this. Like this, all the carriers are overlapped. Even though they are overlapped, there is no interference between the carriers. This is because of their orthogonality property. If you don't understand everything here, don't worry about that, because we are going to cover everything in detail in the future lectures. I am just briefly talking about what happens in OFDM. So that is what written here. The basic idea of OFDM is to partition a high data rate signal, that is x of t, into smaller low data rate signals x1, x2, x3 up to x of n. These are the smaller low data rate signals, so that this data can be sent over many low rate subcarriers. Okay, so here we can see this figure which represent the OFDM. So we have n carriers, f1, f2, f3, fn, and all of them are actually overlapped like this, right? So they are overlapped, still they will not interfere at the receiver because they have orthogonality property among them. Then we will discuss about code division for multiple access, or CDMA. CDMA was used in 2G and heavily used in 3G, a very important communication technique. So how does it actually work? We know that CDMA is a multiple access technique, just like FDM or TDMA. So in FDMA, we are dividing the frequency resource in the frequency domain among the users. And in TDMA, time division for multiple access, we divide the resource in time domain among the users. So each of the user will get a time duration for its communication. Now for CDMA, we don't do any of those things. That means in frequency and time, all the user getting access, but in the vertical axis, we are showing codes, or sometimes it can also be shown as power. So we actually use different unique codes for each of the users, so that they actually don't interfere with each other, even though we are sending all the signals in the same transmission media. So actually CDMA is a subdivision of a technology, spread spectrum technology. It uses spread spectrum technology and a special coding scheme. So if I want to discuss what is spread spectrum technology, let us see that. Now just like before, let's say we want to send a data X in our transmission channel. So in the frequency domain, it should look something like this. So we have the bandwidth like this after modulation. So in spread spectrum technology, what happens is that instead of sending X, we want to encode it using extra bits. That means for X, each of the bits will be represented by multiple bits to encode the data. So obviously at that moment we will have a expanded spectrum, because we don't want to waste any time in the time domain. So we want to use the exact same time duration for the new data. Let's say the new data is x of n. So if I used 5 milliseconds for the transmission of x, we will use the same amount of time for x of n also. As the time duration is fixed here, that means the data rate has to be increased, because x of n has higher data compared to x of n, because we are using extra bit to represent each of the bit of x. So obviously as a result, we will have to use a expanded frequency. In the frequency domain, we will have a expanded view here. That's why it's called spread spectrum. We are expanding or spreading the spectrum in this technology. And as CDMA uses spread spectrum, what happens in CDMA? Let's discuss about that. So in CDMA, what happens is, instead of serving a single user, we can serve multiple users, right? And data of each of these users will get encoded using unique codes, so that they do not interfere with each other. So each of them will have a unique code to encode them, and when they are getting into the transmission channel at the same time, because they are unique and they have a property of orthogonality. This is important. Here also we are using orthogonality. So each of the users will use a special orthogonal codes they will be orthogonal to each other. That's why even though they are in the same transmission line, they will not interfere with each other and be received at the receiver side. So this is the idea of CDMA. So let's move on to the slide again. So in CDMA we use spread spectrum technology, but the code assigned to each of the users are orthogonal to each other. That's why they do not interfere with each other. That's the basic concept of CDMA. Again, if you don't understand everything here, don't worry. This is just the brief introduction of CDMA. Obviously, we will have a lecture prepared later on about CDMA and how it works. Okay, the next one is MIMO, multiple input, multiple output. Now, MIMO is a bit recent technology. It was used in 4G, at the later portion of 4G, and a version of MIMO which is called massive MIMO is being used in 5G. Now let's have a brief discussion about how MIMO works. MIMO basically means that we will have multiple input antennas at the transmitter side and multiple output antennas at the receiver side. So as you can see here, we have a transmitter and n antennas, right, to transmit the data, and at the receiver side we have m receive antennas. So if I want to understand, let's say again we want to send our data x, right? At the transmitter we are trying to send data x, and traditionally what will happen, we will just use one antenna to transmit the whole data x. But in MIMO what we will do, we will divide this x into n small portions. So x1, x2, x3 up to I can say x of n. We have n small portions of data, and using each of the antennas here, we have n antennas here, we can transmit each of the data here. So that means x1 should be transmitted using this one, x2 should be transmitted using this one, like this up to x of n. All the data should be transmitted using n transmit antennas. And at the receiver side, before that, obviously all these data x1 up to x of n will interfere with each other at the transmission channel, right? And at the receiver side, all the antennas, that means starting from this one up to mth antenna, so we have m receive antennas. This m receive antennas will receive the same data that is transmitted by our n transmit antennas. Obviously this is interfered data or corrupted data, there will be some problem. But in MIMO, after doing some mathematical calculations, we actually can retrieve the data properly. That means this x1 up to x of n can be retrieved properly to combine them and finally get the transmitted signal x. So this is the basic idea about our MIMO. So as it's saying here, source data stream is divided into n substream, as I have said, x1 up to x of n, and we transmit that using n transmit antennas. And m receive antennas actually receive those data transmitted from n source antennas. And with a lot of complex math, our receive signal is much better compared to our previous technique, which is single antenna scheme. In addition, this will enable us with a several fold increase in the data rate, because we are doing some kind of parallel transmission, right? Instead of using one antenna, we are using multiple antennas. As a result, obviously our data rate will increase a lot, because instead of sending one data, we are sending a lot of data together at the same time in parallel. That's why MIMO has much higher data rate compared to single antenna transmission. Okay, now non-orthogonal multiple access or NOMA. Now when 5G was being developed, two candidate techniques were proposed. One of them was massive MIMO and another one was NOMA. or non-orthogonal multiple access. Now actually NOMA, even being a very promising technique, the nature of NOMA is very computationally heavy. That's why still to this day our mobile phones doesn't have that computational power to handle the mathematical calculation of NOMA. Maybe in 6G, and that means in 2030 we will have enough computational power to manage NOMA calculations. Now, how does this technology work? It is fundamentally different from other multiple access schemes like TDMA, FDM, or CDMA. We know that in TDMA, FDMA, or CDMA, we have some kind of separation in the frequency domain or time domain, or even using the unique codes or orthogonal codes to separate each of the users in CDMA, right? So here we can see this kind of graph here. So here you see it can be in this axis, this can be time code or frequency, and these users are actually, these different colors are denoting the users. So each of the users are divided among, orthogonally divided among the users, so that they do not interfere with each other. But NOMA is fundamentally different compared to those techniques, because there will be no orthogonal separation between the users. They can overlap in the frequency domain or in the time domain, whatever. So they will be staying in the same frequency region without any orthogonal separation. Still we can retrieve the data for each of the users. All they do is all we do is we distinguish them by their power level. So in this figure you can see that so each of the users are actually using the same frequency, still the power level is different. So maybe for this case these blue users are getting more power here. So using that idea, we have a very complex mathematical process which helps us to find out which user is sending which data. This technique is called successive interference cancellation, or SIC. But the problem is this process is very computationally heavy, and our mobile phones right now don't have that much of capability. So we hope that when 6G will be deployed, we will have the necessary computational power to handle NOMA. Now, as I said earlier, let's discuss about what we plan to cover in this semester. First of all, I want to cover the basics of digital communication, because I know not all of you have taken all the courses, all the optional courses of communication previously. That's why some basic things has to be discussed before we go into the more difficult topics. That's why some necessary topics will be covered in this lecture regarding digital communications and other stuffs like Shannon capacity and Nyquist rate. Then we will see one problem, a very important problem in wireless channel, which is multipath fading effect. And because of that, we have problems like delay spread, intersymbol interference. We will have a brief, very detailed discussion about these problems and how we can actually mitigate them. So one of those solutions is obviously OFDM, which will be our next lecture, orthogonal frequency division multiplexing. And then we will see some of the spread spectrum techniques like DSSS, direct sequence spread spectrum, frequency hopping spread spectrum, and a version of spread spectrum technology which is code division for multiple access, that will also be discussed. And then we will talk about multiple input multiple output, or MIMO, and a version of MIMO which is massive MIMO. So up to now all the topics here are basically techniques used in mobile communication systems. They are not full-fledged communication system itself, but afterwards we are going to see some of the full-fledged communication systems like optical wireless communication systems, wireless sensor networks, and some other advanced communication techniques like Bluetooth, Zigbee, etc. And another one is the software defined radio, which is very important right now, because some of the researches are happening based on these topics, which will be covered also in our semester. So that's it, I guess. That is the course overview. Obviously nothing here is fixed. Some things may change if necessary. That's all for this lecture. Thank you.